let's talk about trig substitution. So trig substitution is a fairly elaborate prescribed process. This chart that you're looking at on the screen is a chart of our instructions for this section. So we have one column that says when you see, something of this form in your integrand, you're going to plug in what's prescribed here. So in this particular one here, we're seeing x equals a sine theta. So theta is the new variable. This is similar to a u substitution where the theta is playing the role of the new variable. So you'll plug in this new situation, factor out the a squared. A squared is whatever number is sitting right here in your integrand. And then simplify what you're looking at with the listed identity here. So we have the fundamental identity of trig kind of moved around, and then a similar one to it. It's another Pythagorean identity in two different arrangements here. These identities always get used in these problems. The identities that are in the fourth column here, it's titled "and maybe also this." These almost always come up. It's very frequent, but they're not necessarily going to happen depending on the details of your problem. But these always will, because they're the crux of the whole method. Okay, so I want you to pause this video and copy down this chart. Once you're done copying down the chart, unpause me. From here, I'm going to start talking about just the top row, and I'm going to do an example of what all of this is talking about. I promise it's not as bad as it looks. Okay, so what we're going to do is zoom in on this first row here for our first example. And I'm actually going to block the rest of the chart with my first example. So we can see this integral fits what's being described here. So the chart says, when you see something of this form in your integrand, we can see here it's not the entire integrand that's set up, but it's the denominator of a fraction here. Okay, so what they're prescribing is to plug in x equals a sine theta, where a is essentially the square root of the number you're seeing here. So that's what I'm going to do, and we'll see how all of this works out. Okay, so a squared equals 4, so the a is 2. I'm just going to write that out to keep my head straight. Okay, so the prescribed substitution is that x equals 2 sine theta. Essentially, anytime there's a number minus x squared, either under your root, or if the root's not there, it'll be like a 3/2 or 5/2 power. Anytime you have a number minus x squared there, this is the substitution you'll make. If instead there's addition between the number and x squared, you'll sub in tan. And then here, if it's x squared minus the number, you choose secant. These are kind of the prescribed 3 choices. And it's all about the identity in the third column. So we'll see that when we get there. Okay, so if we sub in x equals 2 sine theta, we have to do 2 things. So one thing is to compute the dx that goes with it. So I'm just going to, very similar to a u substitution, differentiate this right-hand side. That would be 2 cosine theta. And I'm going to put that d theta on it because I differentiated with respect to theta. So the other thing that I need to do here before I move on to the next step is to write down this restriction on what theta can be. So anytime you make this sign substitution, this first of the 3 options, this is the range that you write down for theta. So you never have to think about why it is what it is. It just automatically comes with it. So we'll write down theta is in the interval minus pi over 2 to pi over 2. And you can see in my chart, I actually have a unit circle visual of what those angles are. It's the right half of the unit circle. The reason that we have that restriction is because it keeps this a 1-to-1 relationship. So the substitution is sound. You could also think of it as the range of arc sine. So this always comes with it, and it's going to have a very important moment in one part, but only that one part. Okay, so for now, we just kind of write it there and ignore it. And now we're in the step where we actually plug stuff in. So I have 1 over square root of, all right, so everywhere there's an x here, I'm going to put 2 sine theta instead. In this particular example, there's only an x right here, but if there was, an x squared up here or an x out front or something, I'd be putting 2 sine theta in all of those spots. Okay, so we have 2 sine theta, and that was x squared, so I have 2 sine theta squared. And then the dx, I'm going to replace with this whole line here, 2 cosine theta d theta. Okay, so it looks like we've made everything significantly worse, but it's all going to work out really, really nice. Okay, so I'm on a simplifying mission right now. The next piece of instructions in the chart say factor out the a squared, which is 4 for us. And we're one step away from being able to do that. What I need to do to see the 4 in both terms is to actually distribute this square. So this is 2 squared sine squared, which is 4 sine squared. As you get comfortable with these problems, you don't have to split up all of these steps. Like this might have been your first line instead of this one. But for now, we're going to take it slow because there's a lot going on. Okay, so both of these terms have a 4 in them, and that's not a coincidence. The reason you put this number here is so that this number matches and that you can factor it out. So that's what I'm going to do. And in fact, if in here we have 4 times 1 minus sine squared, I can actually break it up so that the 4 is under its own root. Right, so square root of 4 times all that under its own square root. 2 cosine theta d theta is still on the outside. This one ends up simplifying especially nice because this square root of 4 is 2, and that perfectly cancels with this 2 over here. So in the next line, the 2 and the root 4 are just going to completely disappear. The next simplifying we're going to do is exactly what's prescribed in this third column. So we are looking now at 1 minus sine squared, and we say, oh, I have an identity for that. That's cosine squared. This is the step that always, always happens. This identity is the reason that we're doing what we're doing. So this 1 minus sine squared will replace with cosine squared theta. Okay, so I'm going to take a step and write what I have before I go too far. Okay, so the 2 constants have canceled. 1 minus sine squared is now cosine squared, and I have cosine theta d theta. Okay, so it's already simplifying quite a bit. It doesn't look quite as bad as it did over here. Okay, and now you can see we're exactly where this 4th column predicted we would be. Okay, so this is the moment that the range on theta becomes important. So the square root of cosine of theta squared, we want to say that the root and the square just cancel each other out, but what they actually do is create an absolute value. If cosine had been negative, when you square it and square root it, now you've lost the minus sign. That's why those absolute values have to be there. So all of this is technically just this. But we say, oh, theta is restricted to only be on this right side of the unit circle. And all of the angles here have positive cosine values because those are the x values. All the negative cosines are over here on the left side. So we say, oh, for this particular choice of theta, we really can replace this with just a plain cosine. Okay, so when we do that here, we have 1 over cosine and then times a cosine here. So this and this perfectly cancel each other out. And my integrand has simplified all the way down to nothing, which is, in this case, really a 1 sitting there. They won't all simplify quite this nice. I chose this example because it came out particularly nice. But the goal is that you'll get something simplified to something down here that you actually have an antiderivative rule for. Okay, so the antiderivative of 1 with respect to theta would be theta. Right, because if this was dx, we would have said x. So if it's d theta, we say theta. And of course, I'll throw in that plus c that's always there. And we're 1 step away from our final answer. We've actually done the integration step. So we just need to switch back to our original variable, which was x. We want to give our answer in terms of x. We're going to do that using the original substitution here. if x equals 2 sine theta, what does theta equal? So we're just going to solve this for theta. I'll divide both sides by 2. And then to undo this, I will arc sine both sides or inverse sine both sides. So arc sine of x over 2 equals theta. And that's what I'm going to put in this spot over here for my final answer. Arc sine of x over 2 plus c. That's my final answer for this indefinite integral. Now, I don't want to end here. I want to come back to this massive chart of instructions and think about why they are what they are now that we've seen this all play out. So if we come back to this chart, so let's look at the second row of the chart. Because there's addition between the number and the x squared in the original problem, we know that like we can make the 4 or whatever number it is have in common and we can factor it out. So we'll get 1 plus the trig function squared. So we chose tangent here because tangent has an identity like this with 1 plus in it, whereas something like sine or cosine doesn't. So that's why we chose tangent, or we will choose tangent here. And then you end up with a secant squared. And then this identity exists for the same reasoning that this one does. So if theta is restricted to the right half of the unit circle here again, this is just the range of arctan. It always comes with this substitution. All of your cosines are positive on the right half of the unit circle, which means secant is also positive. So we can go from absolute value to just regular, and that helps us simplify our problem. And the very last one, we can see, oh, well, eventually when I factor out the number, I'll get trig squared minus 1. So we pick secant as the substitution because secant has an identity with that arrangement, secant squared minus 1. This one, the restrictions on theta are a little bit more complicated. Again, you don't have to, it's really just like a memorizing thing that this comes with that substitution. It's essentially just the first and third quadrant. And again, once you get to the point where you have the absolute value of tangent, which usually comes up, we say, oh, well, in the first and third quadrants, my tangent is always positive, right? Sine and cosine are both positive here, both negative here. So their ratio always comes out positive, and we can continue to make that leap that's so helpful with this simplifying.